The most ambitious energy project in the world today, ITER, which means the way in Latin, is the most complex machine to ever be built by humanity. Its construction involves over 10 million components being built in factories all around the world. Though the extreme nature and complexity of this machine can be highlighted by the number of components, each individual piece is as complex as the entirety of the machine itself. In this series of videos, I will break down its components to its minute level to give you a better understanding of how intricate and precise ITER is, starting with the blanket shield module. The blanket shield is an amazing piece of technology. Each part weighs 4 tons, or about 2 mid-sized vehicles. There are 7 main functions of the blanket system. Provide shielding to reduce heat and neutron load in the vacuum vessel and external vessel components. Absorb radiative and particle heat fluxes from the plasma. Breed tritium to achieve tritium self-sufficiency. Remove energy deposition with high quality for effective power generation. Offer plasma-facing surface, which is designed for a low influx of impurities to the plasma. Deliver limiting surfaces that define the plasma boundary during startup and shutdown. Stipulate passage for and accommodate requirement of interfacing systems. An example, plasma diagnostics. To achieve all of that, the blanket shield is designed in 2 major blocks, the first wall and the blanket shield block. The first wall is by far the most critical component of the machine, hence why a lot of engineering efforts were put into it. Though it looks relatively simple, precision defines this masterpiece. The panels measure 1 by 1.5 meter detachable elements. They are made with 6 to 10 millimeter thick beryllium tiles that are bonded with a copper chromium zirconium alloy and a 316L stainless steel. Beryllium serves a very specific purpose. Since tritium is not readily available and it's also expensive to purchase, breeding is essential. Lithium is used as the tritium breeder. When a neutron from the fusion reaction is released, it encounters lithium located at the breeding blanket wall, which is then absorbed, releasing helium-4 and tritium. One issue is that not all neutrons are absorbed by lithium. To increase the chances of neutron absorption, the blanket needs a neutron multiplier to make the reaction self-sustainable. Beryllium does exactly that, while also being a good heat conductor combined with the copper alloy. The copper alloy layer is designed to enhance heat flux from the plasma to coolant. ITER will be the first fusion device to operate with an actively cooled blanket. Cooling water injected at 4 megapascals and 70 degrees Celsius is designed to remove up to 736 megawatts of thermal power. To do that, the hyper-vapotron concept was introduced. Teeth-like structures are carved at the upper part of the copper layer. When coolant enters these channels, they form vortexes that absorbs heat, allowing for higher possible heat flux. Coolant then flows outward through the stainless steel backplate. The choice of stainless steel serves the complete opposite purpose of the previous 2 metals. First, it acts as a heat containment for the coolant flow, maximizing heat flux efficiency. Second, it acts as a neutron shield for the vessel and magnet coil systems. The first wall panel are made of shaped fingers that are attached to the structural beam that serves as the backbone of each panel and that also houses the cooling water channels. The panels will be attached to the structural shield block by special studs. The access to these studs is located at the middle portion of the first wall. To protect these cavities from radiation and heat, the wall has a slight angle that creates a shadow leading edge. The shield blocks were designed to provide nuclear shielding for the vacuum vessel and coil systems, as well as support for the first wall panels. Cooling water will run to and from the shield blocks through manifolds and branch pipes to remove high heat load expected during ITER operation. These blocks can weigh up to 4 tons and are connected to many other systems, in particular, many diagnostic systems. There are 28 major variants and 150 or more minor design variants. If you look closely, you will notice these slits or cuts all around the block. They serve two purposes: to reduce electromagnetic loads and minimize thermal expansion and bowing. At the back, cutouts were engineered to accommodate the many interfaces, including manifolds or coolant pipes, flexible cartridge, electrical straps, and intermodular pads. One of the major challenges of the blanket shield is alignment. Each shield block must be aligned within a precision of 10 mm globally, and with nominal gap in between neighboring modules of ±4 mm. To achieve that, intermodular pads were designed to be adjustable and extremely precise. 4 flexible axial support allow for compensation of radial positioning. Electrical straps are low-impedance electrical bridges designed to conduct halo currents intercepting some rows of blanket modules. They provide ground paths for all blanket modules and operate as electrical shunts, which protect water cooling pipes from excessive halo and eddy currents. They also need to be elastic to absorb three-dimensional displacement imposed by the machine relative to the vacuum vessel. Lastly, the manifolds are precisely attached to the back, allowing for coolant pipe and other diagnostics wiring. In total, 440 blocks are being mass-produced. On the next video, we will take a look at the second most important component of ITER, the diverter.